Well, anyway, it's a great pleasure to be here. Thank you, Nicholas, for hosting this wonderful meeting in this wonderful city. And it's really wonderful to see many friends from the United States, from New Zealand, and from all over the world. All right, I was going to try and better Ian's Mayor, where is Ian? Mayor of Christchurch. But given the time, I'm going to skip that. You'll have to come to the bar if you want to hear the story about my family who were ruling the roost in Otago. And yet I could just imagine our ancestors arguing about physics-based versus AI-based models. All right, so I'm going to do two things in the talk today around the topic of digital twins. First is I'm going to give you a brief summary on the National Academies study on foundational research gaps and future directions for digital twins, of which I was the chair, just released a report, and I want to give a fairly high overview of that study. Even though the study is targeted towards agencies in the United States, I think for those of you here from New Zealand and from other countries, many of the conclusions and messages in the report are really quite relevant. And then second, I'll give you just a little sort of compressed, a reduced order version of the research talk, show you some of the research highlights from the Odin Institute and from my own group in digital twins. By the way, this is when I gave my TED talk on digital twins, which, by the way, you have to go and watch because we've stalled out at 880,000 views, and my son is trying to get it to 1 million. Right before I came up on the stage, the video guy realized that I had my big name tag on, my behind the stage pass on, and so they tried to get it off me, and it got tangled up in the microphone, and literally they had introduced me and the audience was clapping, and I was having a wrestle on the stage. So if you notice my voice shaking in the first couple minutes of the TED talk, it wasn't just nerves, it was the fact that I literally, it had my head ripped off by the AV guy. Anyway, so there we are, have a deja vu. All right, so this National Academies study on foundational research gaps and future directions for digital twins, you can go to the website there and get all the materials around the study. So this was a study. It was commissioned by 4 agencies: the Department of Energy, the National Science Foundation, the National Institutes of Health, and the Department of Defense. And within the agencies, there were actually a number of programs that supported the studies. You can see here the key questions that the study was charged with asking. Of course, digital twins is such a hot topic and on everybody's mind. But really focusing on mathematical, statistical, and computational foundations and asking the question of what is a digital twin or what is not a digital twin, what are definitions across communities, what are some of the foundational research needs and some of the systemic gaps, what are promising practice across different domains and sectors and opportunities to translate best practices across domains, what are some of the use cases and the success cases for building awareness, building confidence, and ultimately what are key opportunities in research development and application. Really, again, I want to emphasize the focus on foundational research gaps. For those of you not familiar with the National Academies, they're an independent nonprofit that is often commissioned by government agencies to do these independent studies. A big part of the study is information gathering. So the study lasted for a little over a year. Information gathering, which means hosting speakers. We hosted 5 different information gathering sessions, and we also hosted 3 domain-specific workshops, one in the biomedical sciences, one in atmospheric climate and sustainability sciences, and one in engineering domains. And at the study website, you can also see the proceedings in brief, which are basically a narrative capture of each one of those workshops. And I really just want to highlight, if you do go and you look at the proceedings, these proceedings in brief are not part of the consensus output. So you will see comments in there that were made by experts, and those comments are not necessarily endorsed by anybody on the committee, as opposed to the study report, which is a consensus report. And I do say that because I'm going to highlight this in just a second. Through all this information gathering, we heard so many different views of what is a digital twin, what is not a digital twin, what is possible today, what's not possible today, and in many cases, these opinions and perspectives were conflicting, and honestly, in many cases, I think people were making statements that were not right, but they are captured nonetheless in the proceedings in brief. Let me largely skip over this in the report, but just to highlight, the report made 8 8 recommendations, 19 conclusions, 22 findings, and 48 gaps. And if you're working in this area and you have interest in the technical gaps, these gaps are at the end of each one of the chapters of the report, highlighting, certainly not comprehensive, but highlighting some of the places where the study concluded some of the important research gaps lay. All right, so just sort of starting off the bat, and I should also say these slides, or some version of these slides is also at that website, and a recording of the public webinar. Maybe this goes without saying to this community, there is so much excitement and so much promise around the notion of a digital twin, whether you are focused on scientific discovery, whether you are thinking about applications in agriculture, as we heard earlier today, whether you're in the medical industry, just the opportunity for digital twins as a notion to revolutionize the way we do things is tremendous. And in particular, the notion that they are a critical tool for decision making based on a synergistic combination of models and data. So I mentioned, and you saw there in the scope, just this question of how are digital twins defined across communities. And so this took actually several months of the committee's work just to come up with a shared definition of a digital twin. And I'll read to you the definition that we proposed. A digital twin is a set of virtual information constructs that mimics the structure, context, and behavior of a natural, engineered, or social system or system of systems, is dynamically updated with data from its physical twin, has a predictive capability, and informs decisions that realize value. The bidirectional interaction between the virtual and the physical is central to the digital twin. So this definition actually builds very heavily on a definition that came out of a community effort from my own field of aerospace engineering, and aerospace engineering is really the field where the notion of a digital twin comes from. We modified that, we took that definition in the end as a starting point, modified it to make clear that we were thinking about digital twins in the broadest sense. And by the way, just coming up with this language, natural, engineered, or social system, you would not believe, I came to appreciate how words that we use every day, like the word physical system, I use this word all the time. It means something very, very specific to some communities. It means something completely different to other communities. So it was really just a reminder of how important our words are, and we can say something and be interpreted in other ways. But we broadened, we emphasized the importance of a predictive capability, and we really drew out the importance of this bidirectional interaction between the virtual and the physical. And so that definition kind of leads into one of the findings of the report, which is a digital twin is more than just simulation and modeling. And by the way, we heard from some communities in the information gathering, a digital twin is just a new name for simulation and modeling. The committee's conclusion, the consensus was, that is not a digital twin. A digital twin builds on simulation and modeling, but goes beyond it. And how does it go beyond it? This picture, this diagram from the report kind of shows what are the elements of a digital twin. This is what we call the digital twin ecosystem. So over here we have the virtual representation. This is the simulation and modeling, whether your models are grounded in physical principles or they're biological mechanistic models, or they're statistical models, they're machine learning models, all different kinds of models over here in the virtual representation. But this is not a digital twin by itself. We also have here the physical counterpart, the human patient, the aircraft, the bridge, the building, the farm, the natural resource. And very importantly, we have these bidirectional flows. So the flow from physical to virtual, this is where we are taking observations of the physical system, collecting data, and feeding it into the virtual representation so that this virtual representation becomes personalized to the particular physical counterpart that we're tracking, and so that this virtual representation becomes dynamic. It's changing and it's following along with changes in the physical world. So the flow from physical to virtual, then the flow from virtual to physical, where we're now taking this personalized, dynamically evolving virtual representation and using it to drive changes in the physical world, whether that's through control or treatment plans for human patients, or maybe we're using it to drive the collection of data, the experimental design problem. the choice of dynamic sensor allocation, or the choice of where to put sensors in a system. And this flow is sort of dynamic, it's ongoing. Of course, in the middle of it all is potentially a human. Yes, there are some applications of digital twins that may be entirely automated or autonomous, but in many, many situations, there will be a human in the midst of it all. So human-digital twin interaction and human-in-the-loop decision-making are really important elements of digital twins. And then finally, I want to draw your attention to the arrows going around the outside. The topics of verification, validation, uncertainty, quantification, security, and ethics. These are incredibly important topics that, again, they're important in everything we do with computing, but in the digital twin context have really important roles to play and have to be thought of in a holistic way as we think about the other elements of the digital twin. So you saw the definition in words. Graphically, when you ask me, what is a digital twin? To me, it's this diagram and all of these pieces, and not just to me, from the committee, all of the pieces as part of the digital twin. Okay, throughout the report, there are a variety of examples. One of the examples that I think draws out really nicely what all these different pieces are is a cancer patient example. So again, when we talk about the virtual representation, we're talking about all the different kinds of models one could imagine in the computational representation of the system. Issues associated with the physical counterpart, of course, this is patient data collected from all different kinds of modalities. That bidirectional interaction, updating the virtual representation to reflect the characteristics of the individual patient, and then the flow from virtual to physical, informing clinical decisions, both treatment plans and the need to do additional clinical assessments, so new data collection. And then the new clinical assessments inform and update the digital twin. And then you have this sort of what I think is a beautiful graphic in the report, this notion of an infinity loop, the back and forth between the virtual and the physical with those bidirectional flows. Okay, one of the other key findings in the report is that the publicity around digital twins currently outweighs the evidence base of success. And maybe this is something to have a debate in the bar about, but I can see Jim and Doug both nodding. Again, the promise of digital twins is just, it's immense and it's exciting. It's so exciting to think about a world in which digital twins would be helping us to make better decisions. But it is so important that we as a community start to separate out what is aspirational versus what is actual. Somebody mentioned the digital twin of all planet Earth. This is a wonderful aspiration, and it's something that helps to sell the ideas of computational modeling to decision makers, to politicians. But we as a community have to be so clear that we are so far away from actually being able to create a digital twin of full planet Earth at the level of resolution that would be needed to drive the kind of decision making that people are talking about. So separating that aspirational from the actual is so important to strengthen the credibility of digital twin research and to recognize that serious research questions remain. And that's something I think, I hope the report is a call to all aspects of the community to really be very clear on that. And by the way, it's important to have the aspirational and to have that vision, but just be clear on what is and is not actual. That kind of leads into the first recommendation in the report. It's a very long recommendation, and again, it's really targeted towards the federal agencies in the United States, the 4 funding agencies. But the recommendation in spirit says we need an integrated research agenda, and that integrated research agenda includes foundational needs that cut across domains, whether it's medicine or climate or engineering. There are foundational challenges in mathematics, computation, and statistics, as well as domain-specific needs. So again, even though this part of it is sort of targeted towards federal agencies, the message that digital twins to advance, to go from what we can do today to achieve those aspirations requires integration. And I think no matter where you are in the world, this is a really important point. A second piece that really came out, and this goes into the second recommendation in the report, is the need for continual verification, validation, and uncertainty quantification. You saw that as one of the things in the outside loop of that diagram. That is so incredibly important because of the need to establish trust. And by the way, this is not something where we as a community can sort of do all the detailed work and deploy the digital twins and then worry about verification, validation, uncertainty quantification. This has to be built in from the beginning. How do we build trust, whether it's trust from the stakeholders of the system or trust from society more broadly, building trust in the digital twins? What you see there, those are the definitions of verification, validation, uncertainty quantification from the 2012 NRC report that we worked with. And so that led into the second recommendation that VVUQ is critical to the success of the digital twins, and as I said, has to be baked in very, very deeply in the design, creation, and deployment of digital twins. We noted that there are two kind of key pieces that go above and beyond the VVUQ needs we already have for the use of computational tools. One is this notion of the continual back and forth and the dynamic updating. This brings all kinds of new challenges, for example, for validation. Unlike validation of a simulation tool where you go through an extensive validation process and then you're kind of done, now imagine that you're taking this virtual representation and it's continually changing as the physical counterpart is changing. The validation also needs to be done on the fly in a continual way. So new challenges for VVUQ because of that dynamic nature. And then a second point, and this is, I think, an incredibly important point. It's been alluded to a couple of times already in this workshop. It's more than just digital twins. If you think about where we are today compared to where we maybe were a decade ago, there is far, far more use of empirical models, machine learning, AI, neural networks, just generally empirical models in our virtual representations. These pose particular VVUQ challenges. And speaking as an aerospace engineer, just as an aerospace engineer or a structural engineer would never use a finite element model to analyze a structure, and who was talking about trial and error? Well, let's just try it and see if it gives the right answer. We would never do that. We have so much rigorous verification, validation, uncertainty quantification, convergence studies associated with the use of our engineering simulation tools. We need to be bringing that kind of thinking to our AI, to our machine learning tools. This is incredibly important because digital twins will have AI and machine learning embedded in them. They're going to have to be, but VVUQ pose particular challenges there. PSAP, the Predictive Science Academic Alliance Program, was called out in the report. I think it's a fantastic example of how you craft, how a government agency crafts an interdisciplinary program that really incentivizes collaboration and builds verification, validation, uncertainty quantification in as sort of a first-rate partner in the entire concept of the research program. It's PSAP 3, it's in its third generation of centers. So in the report, we called that out as a possible model for other fields to think about emulating. All right, I need to speed up. Another really important conclusion in the report, a digital twin should be fit for purpose. Quite often I will hear people say things like, a digital twin has to be an exquisite replica of the aircraft down to the last bolt on the aircraft. And by the way, we can't do that today, but quantum computing is going to save us and then we're going to be able to do it. Okay. The question of how good is good enough? How much detail do you need to have in your digital twin? Even the word twin, I'm sure in all of our minds, when we say twin, we think of identical replicas, something that looks like the other. I want to remind you all that twins come in different shapes and sizes. In the real biological world, we have fraternal twins that are not identical. So we need to be thinking the same way about our digital twins. Digital twin does not necessarily need to be an identical, exquisite replica of the physical system, but rather should be fit for purpose, balancing the required fidelity that you need for prediction, the available resources, and the acceptable costs. Now, of course, it's very easy to say this. It's very difficult to put this into practice because we don't even have the mathematical and computational tools to truly be able to assess fitness. Is my model good enough to start issuing predictions about the future, particularly when I may be going beyond the data that I've already collected? So this is really a challenge. And also, let's not forget that the available computing resources, which often are going to be at the edge, maybe with communication constraints, maybe with time constraints on how much time you have to make a prediction in order to make a decision, are actually going to drive a great deal of what it means to be fit for purpose. That kind of led to the third recommendation in the study, which is computational resources are a real barrier, and they're particularly a barrier if you happen to be at a national lab, maybe not so much, but for many in the community who could be engaged with digital twin work, computational resources are a barrier, so we need mechanisms to provide researchers with the resources, but at the same time, computing power is not going to get us all the way there. We absolutely need to be investing in mathematical theory and algorithms to reduce the computational needs and again move us from where we are today to some of those aspirations. Okay, I mentioned at the beginning the report sort of went through a whole range of research gaps and opportunities. I'm not going to go through them all here. I'll just highlight for you that some of them are focused research needs and kind of the nitty-gritty of methods and algorithms. Some of them are more systemic, translational, and programmatic. On the focused research needs, we arrange things according to those elements of the digital twin. So in the virtual representation, so many needs to advance the state of what's possible in modeling, and many of them, by the way, involve advancing the state of the art in machine learning and how machine learning can help us to model complex systems with the confidence that we need to drive these critical decisions. On the physical counterpart, again, many challenges around the data acquisition, around integration, interoperability, a huge challenge as we start to think of digital twins of systems. So many challenges on the physical counterpart. Then on the physical to virtual and the virtual to physical flows, again, technical challenges in things like data assimilation, optimization under uncertainty, human-in-the-loop decision-making, and so on. And then last but certainly not least, human-digital twin interactions, user-centered design, ethics, privacy. How do you communicate uncertainty quantification to, let's say, a doctor or a clinician who's going to perhaps be using a digital twin to help inform patient outcomes? So just looking at the words on this slide, you get a sense of all the disparate communities that really need to come together to really advance digital twins. On the more systemic, translational, and programmatic side, we touched on digital twin sustainability, the importance of translation and collaborations, the importance of model and data collaborations, and the critical role of interdisciplinary education, and I'll highlight those just very, very briefly. This is a very important point, and actually I think it's also something that's been touched on in a couple of the talks in this meeting, which is it's really important that we start to think about our digital assets, our virtual asset, our digital twin, as an asset in its own right. So again, go through a thought process. Imagine you're an engineer, you design a bridge, you're a city, you conceive, you design, you build a bridge, and then that's it. You don't have a plan for maintenance, you don't have a plan for inspections, you don't have a plan for upgrades. You just build it and then hope for the best. This is kind of what we do with software, right? So starting to think about the virtual representation, starting to think about the digital twin as an asset, because it is an asset. It's an asset that requires investment and delivers value and serves a purpose, is very, very important and is absolutely critical for digital twin sustainability. And again, I could talk about this for a long time, but just like in engineering, we think about the life cycle of a physical product, the conception, the design, the manufacturing, the operation, and the disposal. We need to be thinking about the life cycle of our digital assets. And I think for many organizations, this really would be a shift in thinking. Recommendations 5, 6, and 7, collaborations are imperative. For those of you who know me, you know I'm a huge fan of everything interdisciplinary. To me, digital twins are the most fantastic interdisciplinary grand challenge that really is going to pull collaborations. So, as I already said, so many challenges cross-cut domains, and I'll tell you about some of the cross-cutting work that we're doing in my own group that maybe highlights some of this. Many advances in modeling, data assimilation, uncertainty quantification, and decision-making have evolved within disciplines. You can look across disciplines and find different names for the same methods that have kind of come up in different disciplines. There really is a need for a concerted effort to look at these advances and to figure out how we could translate across disciplines and come together. We highlighted the importance of model and data collaborations. This is an area where the climate community and the earth sciences really seems to be out in front compared to other domains. And that includes collaboration and coordination with international bodies. And then again, targeting in the US, but I think relevant really worldwide, a need for cross-agency and cross-sector. By cross-sector, academia, government, and industry. Absolutely essential to move forward on these challenges. And then the final recommendation, which was not directly in the scope of the study's statement of tasks, but is so incredibly important. If all of this is going to come to reality, of course you need the people. And so thinking about the interdisciplinary workforce that we need to be creating, both the new workforce and then the upskilling of the existing workforce, both to create the digital twins of the future, but also to be a part of a future in which digital twins are there, is absolutely essential. And so there's a section in the report that talks about workforce needs. So again, so much excitement around digital twins, but an integrated agenda is really needed to harmonize research across sectors and focus efforts on realistic applications. Okay, so that's the first part of the talk, and I'm sure you've got lots of questions, but I think since it's late, I was going to stop and take questions, but I fear that if I stop and take questions, I won't get to tell you about some of the really exciting work that we're doing in Austin. So I've got to keep going. So hold your questions on the report. Let me go very quickly through some of just a couple of research highlights from some of the things we've got going on at the Odin Institute in the area of digital twins. So I want to be clear now, I'm taking off my chair of the National Academies representing the outputs of a consensus study, and I'm now putting on my Karen Willcox professor at UT Austin, director of the Odin Institute. So now what you're going to hear are sort of my own perspectives and opinions, not that you haven't already. I think for many of you, maybe you're not familiar with the Odin Institute. That's the institute that I direct at UT Austin. We are an interdisciplinary institute. You see here our mission statement, or our vision here, advances the field of computational science and engineering and its application to address the grand challenge problems facing society. We have a lot of work that goes on in the mathematical and statistical foundations. We have work in addressing science, engineering, and medicine grand challenges, and then also a little bit less, but work in advancing the architecture algorithm application nexus. So again, we really are a very interdisciplinary institute that blends together mathematics, computing, and physical applications, and we're a sister institute to TAC. So Dan Stanzione, the director of TAC, is here, the Texas Advanced Computing Center. The Odin Institute and TAC both sit in the same portfolio at UT Austin. We just, last year, celebrated our 50th anniversary. In fact, Doug Cothier was one of our plenary speakers at our 50th anniversary celebration last year in September. It's really pretty mind-boggling to think in 1973, Tinsley Odin, who sadly passed away just before the 50th anniversary last year, had this vision that there was a need. He saw the opportunity coming for computing and its impact at that time on engineering problems, and saw the need to create this institute that would bring people together across disciplines. And so 50 years on, we're a lot broader. You can see here some of the topics that we cover. We have 25 different research centers and groups in the institute. We draw together 130 odd faculty from 24 departments across the University of Texas. We have our own PhD program in computational science, engineering, and mathematics. So we have 101 students in our own PhD program, and then another 126 graduate students who are in the departmental PhD programs. So all told, we're several hundred people, and if any of you find yourself in Austin, we would love to host you. It really is an incredible place, an incredible interdisciplinary education construct. Okay, so there's a lot of work going on at the Odin Institute in the area of digital twins, and I'm going to first just highlight a couple things from my colleagues. So Omar Gattas and I are actually co-directors of what the Department of Energy calls a MIMIC Center. This is a multifaceted mathematic integrated capability center. So it's really, it's an applied math center, but again, striving to be interdisciplinary and really driven by Department of Energy applications. And so Omar is leading work in digital twins for next generation manufacturing processes. I myself, so I'm a professor of aerospace engineering, have been doing a lot of work over the years in building digital twins for unmanned aerial vehicles, and really thinking about how digital twins can support structural health monitoring and dynamic mission replanning in uncertain environments for various different applications. We have Mariba Jah, who, if you want to see some entertaining videos, Mariba is what he calls himself a space environmentalist. He's a real advocate for the need for the globe to start managing the mess that's going on in space. So he has been doing a lot of work to build a digital twin of Earth orbits and to start tracking and dealing with the space junk problem. I think it's just fascinating, again, to think about the range of opportunities here for digital twins. On the more geosciences side, so those examples were all drawn from engineering. On the geosciences side, again, Omar does a lot of work in modeling ice sheets. So this is a full-scale model of Antarctica. And then Patrick Heimbach, this is a beautiful visualization that actually was done together with TAC's visualization team of the ocean ice sheet interactions at the continent level and around Greenland. And again, you know, I know there are probably experts here, but opportunities for thinking about how you take the very sparse and expensive data, and yes, we live in the world of big data, but the measurements, the actual data that you have about Antarctica or about what's going on in the Arctic are so sparse in both space and time, and so expensive to acquire. How do you take that data, how do you put it together with the horribly inadequate models that we have to drive critical decisions, billion-dollar decisions about, for example, where to drill the next ice core at Antarctica? This is such a great opportunity for this notion of digital twins to really, I think, drive decision-making around climate. And then finally, medicine, and this, I don't know, I'm excited about all these things, but medicine is maybe where I see the nearest term impact for digital twins. And again, you know, what I just said about the geosciences, thinking about medicine where we have such limited data. When we get sick, we don't really know what's going on. We have limited measurements. We have imaging, looking from the outside in, trying to figure out whether we have a tumor or how quickly it's going to grow. So we have imperfect, sparse data. We have imperfect models, inadequate models. Biologists are really starting to understand some of the foundational mechanisms in things like cancer tumors. How do we put all those together and put them in the hands of the clinicians to drive better decision-making for individual patients, decisions that are targeted to you as an individual instead of based on population data? This is a place where the notion of a digital twin really can come to the fore. Within the Odin Institute, we have the Center for Computational Oncology. Tom Yankelov leads that. And the Wilson Center for Cardiovascular Modeling and Simulation, led by Michael Sachs, both of whom are doing a lot of work in digital twins for these medical applications. So in the very last part, and I'm doing well on time here, I better slow down. No, I'm joking. So in the very last part, I want to give you a little bit of a snapshot of some of the work that's going on in my own group. And as I talk through this, I want to remind you guys, I am an aerospace engineer, trained as an undergraduate degree from engineering science at the University of Auckland. I'm trained as an aerospace engineer. The vast majority of my work is on systems related to aerospace. But I'm going to tell you about some of the work that my group has been doing together with the Center for Computational Oncology at the Odin Institute in taking the methods that we developed for building a digital twin of an unmanned aerial vehicle and bringing those methods over to develop a digital twin of a cancer patient. And it's, again, I get excited about everything. I don't want to say this is my favorite project, but it's one of my favorite projects at the moment, in part because it shows the power of abstraction, of mathematics and computational abstractions for cross-cutting domains, and in part because as excited I am about things that fly and go into space, using mathematics and computing to actually improve outcomes with cancer patients is also pretty exciting. So, and I have to ask, are there any doctors in the audience? Yeah, because usually I'm giving these talks and I have to, if I say anything wrong, you have to remember I'm an aerospace engineer, but you hear an aerospace engineer's interpretation of what goes on. Okay, so radiotherapy regimens for high-grade gliomas. So we're talking about brain cancers here, and these are brain cancers that progress very quickly. So what we're looking at here is what's called the standard of care. So if you or someone in your family has the unfortunate occurrence to be diagnosed with one of these high-grade gliomas, here on what we're calling day 0 is an MRI, so an image. And so this is post-surgery. And then again at day 20, there would be another MRI taken. And at that point, the radiotherapy planning would start. And the standard radiotherapy regimen, again, what's called the standard of care, is to get 2 grays per day, gray being the measure of radiation, 2 grays per day on Monday, Tuesday, Wednesday, Thursday, Friday, and then Saturday, Sunday off for 1, 2, 3, 4, 5, 6 weeks, so that every patient receives a total of 60 grays over the course of 6 weeks, again delivered at 2 grays per day. And then that would stop, and then a little ways longer at day 152, that's the time horizon for what's called the time to progression assessment. The time to progression is how many days until the tumor comes back at some particular level, and then some kind of a follow-up observation. And so probably you're already thinking, right, the question is, can you imagine what could a digital twin do in this situation? And again, let's be clear about the actual versus the aspirational. But the aspirational here is that you would come in, and instead of it being the standard of care, which means it's applied to all of us the same, it's patient-specific, so that as we start to conduct these MRIs, we can use them to build a digital twin that is calibrated to our own anatomy, to our own material properties, my brain versus Nicholas's brain, let's not get into that debate, and come up with a patient-specific optimized radiotherapy regimen, one that balances the outcomes, but also thinks about things like the toxicity and how the patients are going to respond. So in the study that we've been working on, the setup is the one that you see here, where we've got the MRI here at day 0 and day 20. We're using an extra MRI at day 27. That's one that we are using to calibrate the patient's response. You can see here in the first week we use the standard of care, and then that third MRI is again calibrating the parameters of the model that represent the patient's response. And then from weeks 2 through 6, the orange little dots here, the little bars here, represent a patient-specific optimized radiotherapy regimen. So this is still a pretty structured setup. I mean, you could imagine really moving to optimized regimen, but this is the study that I'm going to show you. All right, so this is sort of one slide of all the technical work. So again, I mentioned the work that we had done to build digital twins for unmanned aerial vehicles. That's the first paper up there. So Michael Kaptein was one of my PhD students. He has a work there published in Nature Computational Science, where we proposed a probabilistic graphical model as a way to do a mathematical abstraction of a digital twin. I'm not going to go into the details, but the idea is that you formally lay out what is the state, what is it you're trying to track, what are the observations, what can you observe about the system, what are the controls, what are the decisions that you can make, what are the rewards, how do you decide whether one decision is better than another, what are the quantities of interest, what are the things that you want to predict out into the future, and how are you going to represent all of this with models. So we took all of this, we put it formally into a graph, into a probabilistic graphical model, and maybe the 2 important things to take away from why a probabilistic graphical model is that One, what do we know about graphical models? What do we know about graphs? Graphs are mathematical entities where the relationships are just as important as the nodes. The edges in the graph are just as important as the nodes. And as we think about digital twins and what they represent, this integration of all these pieces, it's a situation where we have to be modeling the relationship among the pieces of the system. So that's number one with a graph. And number two, a probabilistic graphical model, everything in here is modeled as a random variable, which means that we're baking the uncertainty into the formulation of the digital twin right from the beginning, because again, we're operating in these complex systems where the data are sparse, indirect, noisy, and the models are inadequate. So we're baking in the uncertainty quantification from the get-go. So Michael and I developed this work in the context of aircraft, and again, the really exciting thing is that we were able to work with Tom Yankelov's group and take that mathematical abstraction and bring it over. And by the way, it turns out, I had no idea, the state of the art in modeling tumors, they actually turned out to be reaction diffusion equations, which are the kinds of equations that I use for modeling the what goes on inside a rocket engine in combustion. Now, the form of the reaction term is different. Obviously, the physics and the biology are very different, but these are partial differential equations. And again, back to the earlier point and one of the findings from the study, at some level, these systems are so different, but there are so many common mathematical challenges. So the Frontiers in AI paper referenced there, that was the first paper that we have on this cancer patient work. So I'm not going to show you too much. I will tell you it's a very simple model for the tumor, for the brain tumors that we started with. But again, just to give you a sense of the challenges in these problems and why, first of all, it's important to include uncertainty, and second, this digital twin thinking, this integration of models, data, and decision is so important. This is the patient prior. So before you've seen any patient data, in our simple model, we have these 4 parameters: proliferation rate, carrier capacity, radiosensitivity parameter, and initial tumor burden. This is the initial conditions of the tumor. This is a parameter that describes how you as the individual patient respond to the treatment. And then these 2 things here relate to things that go on in your body that are going to determine how the tumor grows. So these are distributions, and these are distributions coming from actual patient data. And right, you can see you probably can't even read the numbers. You can look at those and you're like, okay, I don't really know, is that a lot of uncertainty? So we can take those distributions, those ranges for each one of these parameters, and we can push that uncertainty through the model and say, predict the tumor cell count versus time over this range of parameters. And so what do we see here? The tumor is growing, and then the radiotherapy, the standard of care, is starting. You see these little zigzags here. That's because of the way the radiation is delivered in the standard of care. And then it comes down, and then the treatment stops. And then, maybe you're looking at the dark line here, maybe the tumor cell count holds down for a while, and then it starts to grow at some point. Okay, so the dark blue line there is the mean prediction from the model, and then the blue band is the uncertainty associated with the fact that we don't actually know what these parameters are. And if there's one thing you take away from this chart, you look here after the treatment ends, and you say, we have no clue. We have no idea what happens. Right. And so, again, this is a situation, and I'm forgetting the context of where this came up. Somebody said we don't have to be perfect to be deploying things. This is a situation where even if the digital twin is never going to be an exquisite replica. It's never going to be perfect. You look at how much variability there is from patient to patient and how much uncertainty that translates into the decisions that the clinician makes, and you say that if we could put the data and the models together, maybe we could do better. So that's what we do with our favorite Bayesian methods that sit on top of the probabilistic graphical model. So what you're seeing now here is patient 1, and by the way, our patients and what I'm showing you here are notional patients. We take patient 1's data, we do the update. There is still uncertainty because we cannot observe carrying capacity. What you have is MRI data. You can try to infer those parameters, but it's indirect. So there's still uncertainty. And in fact, you can see for some of the parameters, the data actually really doesn't tell you very much about those parameters at all, whereas for others, you do start to nail them down. So you can now have the posteriors, the patient-specific posteriors, they're in orange. Now you can take those reduced uncertainty distributions, again, push them through the model, and now you start to see, yes, there's still a lot of uncertainty out here in what might happen, but we have reduced the uncertainty quite a bit. So there's patient 1, there's patient 2, and patient 3. And again, these are notional virtual patients. And as I go between them, again, what you should take away is that, and even though these are notional, they're representative, there is so much variability from patient to patient. If you look at the distributions and you see where the parameters are getting kind of fixed into, so much variability because we are so different as people. And by the way, this is a place where maybe the airplane and the humans differ. So a ton of variability, and that translates into a lot of uncertainty in the outcomes. Okay, this is the last slide, but again, just to sort of give you a sense of how all of this can be brought together. So what we're looking at here now are the Pareto plots for patient 1, patient 2, and patient 3. So we're plotting on the y-axis here the time to progression. So remember, this is a measure of how long it takes for the tumor to come back. So a long time to progression is really good. On the x-axis here is the total dosage. So remember when I talked about the standard of care, it was 60 grays total for everybody. Now you could give more dosage to people and have the tumor be more aggressively treated, but of course with more radiotherapy dosage comes additional side effects and other adverse outcomes. So there's a trade-off here between the total dosage and the outcome in the time to progression. And what you see here is the standard of care for the 3 patients. How well did they do when they got the standard 2 grays per day? And then the orange lines here are the outcomes of this now optimized patient-specific regimen with a simple model, but with this digital twin paradigm. And what it says, essentially, is that you could keep the same total dosage, 60 grays, and achieve better outcomes on the time to progression, or you could achieve the same time to progression as standard of care, but reduce the dosage so that the patient was not as sick during treatment. And by the way, there's a trade-off, and the trade-off curve for every patient is different. And so now you could imagine sort of rolling this up into a tool and presenting this to clinical decision makers and using them to guide decisions. And so in the next phase of this work, we're working to make the models more sophisticated, and we're also collaborating very closely with MD Anderson Cancer Center, which is also part of the the University of Texas system, to sort of take this to the next level and actually maybe be able to get this into the hands of the clinicians. We have a clinician, a doctor who is fantastic, who we work with. So maybe get this out into the field. Very exciting. All right, so with that, Nicholas is standing up, which is good because I am done. Again, I have told you about 2 distinct but related things: National Academies study and the sort of the survey at the high level of what we concluded there, and then a little bit of a snapshot of what goes on at the Odin Institute and what keeps me busy at UT Austin. But with that, I want to thank everybody for sticking with me. Thank you.